2010. We launched our first product in 2013. Now we are around 30 people, engineers, and we're based in Montrouge, so quite close to here. You can go through metro when there is no street. Now you probably know this type of infrastructure. So these are regular data centers. So it can be Facebook, Amazon, Microsoft, Google, so all the big companies, huge building in the suburb, and in these buildings, like thousands of computers that you can run your computations on. And these infrastructures are obviously very useful, but they have a few drawbacks as well. First of all, you need to build them. These huge buildings obviously cost some money. You need to power them, all these processors to run your computations. And then you need to cool them, because as you probably know, like computers, when they run like heavy computations, they generate heat in these buildings that have like thousands of them. It's a huge problem, and you need to spend a huge amount of energy to cool them, to cool them and be able to use them efficiently. It's a problem, obviously, for ecological reasons. You spend energy that you could avoid to spend. It's also a problem on the economical part, because you spend a lot of money for this energy. So just in France, the electrical consumption of data centers represent around 3 to 4% of the national consumption, and it's meant to rise with like a lot of new services coming, like autonomous vehicles, etc., etc. So with Qarnot, we try to solve this issue, and with our solution, we managed to have something much cheaper and much greener as well. So like compared to these classical services, our computation will be around 3 to 4 times cheaper, and it will only emit 25% of the carbon that a regular data center would emit. So how do we do this? That's the big question. So this slide sums it up generally. So our big concern is to only install our infrastructure or computers in buildings where the heat can be reused. So where data center, the heat is just lost, it's a waste. We install infrastructures in housing where people need heat, like today. It can be in offices, it can be as well in warehouses where employees have to work on a daily basis. So we have all our infrastructure, and at the top of this, because we want it to be very simple to use these infrastructures, we have a platform called Qware that I will introduce a bit later, that makes it extremely easy to have access to this infrastructure and to run parallel calculations, such as the one of FreeFEM. So now I'm going to go a bit more into details about our infrastructures. Our historical product is called the computing heater. So as you can see here, it's a natural environment in a house, and it really looks like an electrical heater. You can choose the temperature with buttons or through an app. It can be automatized, etc. But if you open it, you can see that it's completely different from a regular heater. And what you see here are several processors that are stuck to the heatsink. And what will happen when you run your FreeFEM computation through our platform or API, it will launch, or it will like send computation on this infrastructure. It will run on the processor. It will generate some heat. This heat will be transferred to the heatsink and then to the air, and it will help warm family or employees. And then obviously the output of your computation will be sent back to you. Then we developed the second product. It's the same principle, but without the fancy frame. Here you can see that all of these computers are in a warehouse, so that's why you don't really need all the fancy frame like the electrical heater I just showed you. And we recently created a joint venture with a Casino Group. So as you might know, they have a huge amount of warehouses in France. This is in the south of Paris. We installed 20,000 cores in an empty space of the warehouse. They're like running a computation. It generates heat that is used for the employees and for the whole warehouse. For us, it's a great advantage because we can deploy new installation extremely quickly. We already have some different warehouses where we know that we can deploy 20,000 cores within a few months. And finally, our last product in terms of infrastructure that we launched a few weeks ago is the computing boiler. The concept is a bit the same as the computing heater, but instead of heating air, you will heat water. I'll go a little bit into details in what's happening. So you have cold water coming in, then this cold water will go through like pipes that are in several aluminum plates, and these plates are sticked against processors. I'll show you a picture just after. You have like 24 CPUs, can be as well GPUs and CPUs, depending on the needs. And in our infrastructure, we essentially use AMD Ryzen CPUs for those who know. And so it goes through all these different aluminum plates. We managed to put 3 kilowatt of energy of heat, so therefore heat through this water, and at the end you get hot water. And depending on the input temperature of the water, you can get something up to 65 degrees. And this is how it looks like in the real life, with the aluminum blades that are here and all the processors stick to it. Now I'll discuss a bit more about our software, our platform that will make it very easy to use or to run computation on these infrastructures. So it's called Qware, and the goal is really to, well, as I said, to be very flexible in terms of the usage of our infrastructure. So what you do is that you run a computation, for instance, a FreeFEM computation, through the API, and with a few lines of code, you'll connect to the to the main server that will dispatch your computation where it is available. So it can be a heater, it can be a boiler, it can even be like a private or public cloud. You don't really need to know about it. The only thing you want to is to connect easily through our platform. So what is called in the business is the platform as a service. It's not infrastructure as a service, because you don't need to take care of by yourself or put like making run your computation on the infrastructure. The platform will dispatch your computation by itself. It's very flexible, so we mentioned containers earlier, so you can run any application that you want on our platform. You can take a Docker image that is already existing. You have the one of FreeFEM that is available on the registry. You can make your own or take one already existing. And we try to make it as simple as possible to use. So within a few lines, you can connect to the API, etc. We have SDK in Python, C#, and Node.js. And as well, we want to make it very user-friendly. So there is a console that my colleagues will show you later, where you can like monitor your task. You can also start a computing task from there, stop it, monitor it, see how it goes. And here's a quick example of some lines, and just these small amounts, I don't know, 6, 7 lines are enough to launch your computation. So see the first line, you import the SDK on the machine, then you connect to the API through a client token. So whenever you create your account on Qarnot, you'll have like your own token with the credits available. You create your computing tasks. So here you give it a name to be Fibonacci. Then you decide like the type. Here is Docker batch, the number of instances you want to run. So here you have 40 chunks for this. Docker repo, you can add like basically some constants to your computation. One of the constants will be the Docker image you want to use. Here it's called Python, so we imagine it's just an image in Linux and Python on it. And then the command you want to run in your container. And here it's like basically a computation to print some Fibonacci numbers. Then task.run, and that's it. You're done. The rest of the work is on the platform. It will like, well, I'll show you actually. Here's what we'll do. It will connect through the API to the Qarnot. So these servers are in the data center. They will check the availability of our different resources. Then it will send your computation to the proper building. In the building, you have another server. Let's say it selected this Qbox. We call it a Qbox. And this one will do the same job, checking the availability, for instance, of the different heaters and the different CPUs in the building. Check the one available, send the computation to it. It runs, and then you get the output through the other way. And finally, the ecosystem that we try to develop. So historically, our main computing clients were banks. So most of the French banks now have some of their risk simulations running on our platform. But recently, we decided to create a new team, so it's called the QLab, and I'm part of it with Ariane and Victor that will do the tutorials just after. And the goal of this team is to really explore new branches, new scientific domains through the prism of computing science, or computing in general. And for this, we need to do several things. First of all, we want to be really concrete. It's very easy with high performance computing to be a bit too abstract. We try to do the opposite, to show pictures, to be very concrete, show visualizations. Then we want as well to understand well the people we talk to. So if it's finite element multiphysics, try to really understand like the different issues, what they need in terms of computing, etc., understanding the jobs we work with. And then we also have a specific focus on open source software, so we try to discuss with all the different communities. I'll give you some examples later. And at the end, trying to discuss with everyone, research and development labs or departments, open source communities, labs, and eventually make them interact together, maybe through some events of this type. So as I said, historically, we were working with banks essentially. Then we developed new branches. We started to work with 3D animation. So as you might know, 3D animation is extremely needy in terms of computing. So just a picture like this one needs approximately 1 hour of computation. So you can imagine for a movie what it is. So we have partnerships with several animation studios, and we most of the time go through Blender, which is a famous open source software. So we have this, Ariane here is the professional of 3D animation in our team. Then we're also very proud to have this partnership with FreeFEM, and we understand more and more about it. Victor is our local expert for finite element method. And yeah, we're very happy to provide all the computing power necessary for all the tutorials that will come today and tomorrow. So just so that you know, we booked 40 CPUs with 16 cores each in a specific building. So that represents almost 500 cores, so that should be largely enough for all the computing we'll do today and tomorrow. And what's coming after this? So we're exploring a lot of different branches. So it can go from chemistry with molecular docking, which is necessary in the drug design. We are doing fire simulation. So we have a partnership with another lab here in Jussieu to reproduce or simulate the Great Fire of Rome in the 1st century. So what you see here is a burning temple. And yes, studying a lot of other open source software, so going from MapReduce to fluid dynamics and machine learning, etc., etc. So a lot of things to come. And that's it. Thank you very much for your attention, and I'm ready for any question as well. Any question?
As you see that nobody want to speak. So I think when you try, you have some question in a few minutes.
So yeah, as Frederick just said, just after Victor and Ariane will show you some more tutorials so that it's as concrete as possible, and you run some FreeFEM computations on our platform, so it might be more visual for you. Yes?
After computation, we have sometimes with data from the time dependent case. How to extract and get the data from the system?
So there is a storage going with it where you can put like input data, to run all the computation, and then you can gather the output data as well.
So if the computation may fail for some reason, and the some idea of restarting is normally recommended in the system, the university, some batch system. Batch system sometimes they guarantee the restarting of the computation. How about the such kind of
So we have two types. Either you can go through batch, either you can go through connected to the network, that we don't necessarily recommend, but you have the two options. Maybe Paul, you want to add?
In fact, you have a system for storage. You have a S3 standard system based on Ceph. And in fact, the platform guarantees the restart of nodes if for any reason a node stops. But if it's a problem with the software or with the data, we can just give you a snapshot of the data, but you have to describe the fact that you want to snapshot the data, make your own breakpoints.
Any other questions? Yes.
What is the largest number of cores, for instance, somebody has used on this?
Oh, historically?
Yeah, I mean, just one thing.
I would say it's a cluster from a bank.
A bank using about 5,000 cores, but it's mostly batch computation.
Okay.
So it's mostly embarrassingly parallel batch. Today the biggest nodes we operate are about 32 cores. next year probably 64 cores, but we are not sure yet. And maybe tomorrow we interconnect with supercomputers. We cannot.
All good.
So, thanks
Thank
again.
you.
I think now it's time to split